Good afternoon and greetings from Indian Institute of Remote Sensing, Dehradun. I'm Dr. Arijit Roy, and I will be talking to you about the use of geospatial technology for climate change studies. So what do we understand by climate? And what is the importance of climate? See, the atmosphere which we talk about and which we all experience is a global common. And air over one place is typically halfway around the world in a week's time. And this has been proved by various experiments, mainly the manned balloon flights. And if we see, this atmosphere has now become a dumping ground. In fact, it's for all the nations who are polluting these atmospheres with all sorts of pollutants. And some of these pollutants last a long time. And the effects of these pollutants are shared by all. And these pollutants have caused a serious consequence, which we all know as the global warming. So what is global warming? It is the observed increase in the temperature experienced over the last century, and it's mainly due to the dumping of the pollutants, mainly from the fossil fuels and other sources into the atmosphere. And the fourth assessment report, way back in 2007, has clearly stated that this global warming is very likely of anthropogenic origin. So the temperature is increasing across the world in the last 200 years, is a scientific fact. And the temperature increase across the world in these last 200 years has been measured. So there is now scientific evidence, which is quantifiable, that there is a significant increase in the temperature during last 200 years. It's also observed that this temperature change is not the same over the world. In fact, in the polar regions and in the higher altitudes, the temperature increase is significantly higher than those in the tropical regions or in the warmer latitudes. But even if we take the global average, it is there is a significant variability which actually enables us to assess that it has actually increased. And in the assessment report 5 of IPCC, the reason of these changes in the various pollutants in the atmosphere, because of which the global warming is taking place, has been somehow quantified. And it is basically based on the measure of the net change in the energy balance in response to the external perturbation. And these external perturbations are mainly caused by the changes in the atmosphere, the ocean, the biosphere, and the cryosphere, because of the various anthropogenic activities. And these are identified by the changes in the net effective radiative forcing, which accounts for the rapid response in the climate system. And what we basically mean by the effective radiative forcing is the change in the net downward flux of the solar energy or the energy at the top of the atmosphere after allowing the atmospheric temperature, water vapor, clouds, and the land albedo to adjust. And this basically involves the various feedbacks which either amplify or diminish the effect of the changes in the climate forcing. And in the assessment report 5, they have basically considered the representative concentration pathway and their changes. So there were 4 greenhouse gas concentration trajectories which were identified in assessment report 5. And depending on how much greenhouse gases are emitted in the years to come, the 4 RCPs, that is RCP 2.6, 4.5, 6, and 8.5, are named after a possible range of radiative forcing values in the year 2000 relative to the pre-industrial values, which is the net effective radiative forcing is exceeded by 2.6 watts per meter square, 4.5 watts per meter square, 6.0 watts per meter square, and 8.5 watts per meter square, respectively, across the globe. It's basically an average. And if you see the historical and the projected total anthropogenic radiative forcing relative to the pre-industrial time, that is 1765, which has been taken as the baseline. So the net anthropogenic radiative forcing between 1950 and 2100 shows a significant increase. And there are many experimental and quantifiable measurements which are available to validate this fact, which actually enables us to say that the warming of the climate system is unequivocal. And since 1950s, many of the observed changes are unprecedented over the decades to millennia. The atmosphere and ocean have warmed. There's evidence about it. The amount of snow and ice have diminished, mainly in the poles, and we are basically observing it through space-based observatories as well as the ground observation. And there is a significant change, or the sea level have risen. And we all have estimated basically that the concentration of greenhouse gas have also increased. So if we see the global map here in the right, we see that there's an observed change in the surface temperature between 1901 and 2012, that's last century. Some areas have shown significant increase, while some areas have shown a normal increase. And the areas which have shown significant increase are the subtropical region and some areas of the Amazon, which has basically shown a significant increase because of the deforestation which has been carried over the last century in this region. And why this is increasing is because of the total anthropogenic radiative forcing relative to the 1750 baseline of the pre-industrial era. So if we see the total anthropogenic radiative forcing in 1950s, it was around 0.5 watts per meter square increase, which increased to more than 1, that is around 1.25 by 1980. And in 2011, the total anthropogenic radiative forcing increase with respect to the pre-industrial era is more than 2.25. And this is significant because this is going to change, basically change many of the systems beyond the tripping point. So what are basically the drivers of the climate change? They are or what are effective, basically the drivers which are causing a change in the radiative forcing. They are the various greenhouse gases, both long-term, like carbon dioxide, methane, halocarbons, N2O, as well as the short-lived gases like carbon monoxide, NMVOCs, NOxs, aerosols, and their precursors, etc. So, most of them have got a significant positive impact on the net radiative forcing, while some of them like albedo and some of the nitrate compounds, they have negative radiative forcing, but they change. So we are at a position that we can expect a net global warming of 1.5 degrees centigrade with the amount of pollution we have already pumped into the atmosphere. In 2015, it is estimated that the human activities are estimated to have caused an approximate 1 degree centigrade of global warming above the pre-industrial levels. And this is likely to reach between 1.5 to 2 degrees between 2030 to 2052. If it continues to increase at this rate, and this is speculated or projected with a significantly high confidence. So you can see the cumulative emission of CO2 and future non-CO2 radiative forcings, which can lead to a warming of 1.5 degrees centigrade. So in effect, we can safely conclude that the global climate is changing, and the fossil fuel use is playing a large role in driving this climate change. And this has resulted in the greenhouse effect, increase in greenhouse gases, and the disruption in the carbon cycle. So what are the geospatial technologies for studying these changes on the Earth's surface, which affect the radiative forces? The prime among them is the land cover changes, followed by the changes in biophysical properties, the changes in the cryosphere, and their influence on the coupled climate models. So when we talk about space technology, which can be used to monitor the climate change, what can space technology do, or Earth observation systems provide? They help us to observe the weather conditions, the meteorological observations. And among the Earth observation applications, they help us to identify the crop production and yield forecasting, estimate the water resource assessment, the bioresource assessment, the minerals, soils, and gas exploration, and disaster management support. Apart from this, they also provide information in the various environment and the climate research, like information on the atmospheric chemistry, pollution, etc. So, when we talk about Earth observation system or satellite-based remote sensing, data processing, and data reception, satellite system provides information on the topography, soil, land cover, and vegetation. Then meteorology observation, which help us to provide modeled as well as the observed information on the various meteorological parameters like temperature regimes, the precipitation regimes, the humidity profiles, etc. And we also information on the various observed land states like snow, evapotranspiration, soil moisture, groundwater, carbon, etc. from the ground systems. And all of this information, when they are combined in a geospatial domain, help us to understand the various complex systems which are in process across the Earth, like the land surface model, understand the physical process models, various climate models, the catchment characteristics, the landscape mosaics, etc., as well as help in the data assimilation modules of various physical-based models like the meteorological models, the climate models. And all this information, all these databases basically provides information on the various processes like the energy flux, the biogeochemistries, which is the biogeochemical cycles like carbon, nitrogen, etc. The water fluxes like runoff, the hydrological regimes, etc. And the surface states like moisture, total carbon, etc. Which help us to identify or predict the water supply and demand, the potential of agriculture and hydroelectric power generation, the state of our endangered species, water quality, and various improved short-term and long-term predictions. So when we talk about the climate models, we have covered a lot of areas. Earlier, it was the climate models were very simple, which took into account the atmosphere, land surface vegetation, and the ocean in 1960s and 70s. With the advancement in the computation capability and the growth of supercomputers, we basically ventured into the coupled climate models and also started integrating the various other factors like sea ice. As we progressed, we incorporated the components like the aerosols, dust, sea sprays, then how the vegetation interacts with the climate using DGVMs, then sulfate aerosols, the biogeochemical cycles and the carbon cycles were integrated. And in the last decade, we basically started using the various other aspects like upper atmosphere, the atmospheric chemistry, the ice sheet, marine ecosystems, and various other components which have gone into the models and made it actually very complex. But their accuracy is also increased because of it. And the capability which we have now is that we have got a very, very high resolution. We have improved upon this resolution to a great extent. Earlier, we had the models output at around 100 kilometers by 100 kilometers, or 1 degree by 1 degree. During, say, 1970s and 1980s, even 1990s. And now we have improved this with the various advancement in the regional RCMs, the regional climate models, which include all these aspects. So we have basically been able to understand our climate system much better. And we are still in a process of understanding them. And the inputs in all of these models, like the extent of sea ice, the sulfate aerosols, solar forcings, carbon nitrogen cycles, the dust aerosols, the vegetation interaction, the biochemical cycle and ice sheets, all these inputs basically go from the Earth observation systems. So now I'll be just going through a few examples of how we are using the Earth observation system for identifying the impact of the climate changes on the various ecosystem processes. Like the crop productivity, for example. Various models have actually shown that due to the changes in the climate, there is going to be a significant changes in the final yields, mostly of the various horticulture crop as well as the cereal crop. Then the long-term normalized difference vegetation index studies, there is various vegetation index studies over the various regions. I have taken the case of Himalaya as we are in the vicinity. They have shown there is a distinct reduction in the greenness in this Himalayan region. And the greenness is not because of the area which has been denuded or something like that. It is because of the significant delay in the onset of leaf flush and early leaf fall. So the amount of time the vegetation is green in the Himalaya has reduced significantly. And we have been able to identify various areas which have shown distinct browning because of the various climate as well as I would say anthropogenic induced forcings. Another area where we have got we basically have achieved significant success is to model how the various vegetation and species are going to shift in the Western Himalaya under climate change conditions, using a complex algorithm which include a number of models to see how the various vegetation communities are going to interact and react in the climate change scenarios. So what we have seen is that because of this, a number of species are going to disappear. The communities which are prevalent now, like the moist temperate regions, which have a huge, significant biodiversity, are going to lose their community structure. So this community, which were earlier composed of something like 10 to 15 dominant species, will have just 3 to 4 dominant species, with the rest of the species disappearing from that community in that area. And there is a visible reduction in the potential distribution of the species, especially like species like Betula or the Bhojpatra, as we know, in 2050 and 2080. Then there is a significant change in the nitrogen. As we have seen, nitrogen cycles is a significant in climate change impact. So spatial distribution of the vegetation nitrogen can also be derived or retrieved from the Earth observation systems. And using various techniques, including hyperspectral remote sensing, we have been able to accurately extrapolate and extract the nitrogen content on the vegetation in a particular area. Another area which is very, very important when we talk about the vegetation and the migration of the species is the connectivity. So how do we estimate the connectivity? There are two types of connectivity if we talk about it. So one is a structural connectivity, where we have the actual connectivity in form of vegetation cover. And another is a functional connectivity, which is based on the dispersal potential of an individual species from one patch to or one natural area to another natural area. So this helps us in identifying the species migration potential, how the local species extinction can happen in that area because of the changes in the bioclimatic regimes as a result of climate change, how the changes in the ecosystem energy and nutrient flow can be affected in case of fragmentation of the habitat, as well as the potential for invasive species in a particular area. And using various mathematical tools like graph theory, circuit theory, or least cost path, we can very well carry out this analysis. We all know that in the higher reaches, especially in the Himalaya, there is a phenomena which is known as tree line. There is a particular elevation beyond which the trees are not able to survive because of the extreme harsh conditions, mainly the cold conditions. So this is basically known as a tree line. It is observed in that in many of the regions of Uttarakhand, especially the Nanda Devi Biosphere Reserve, where there is very less human anthropogenic impact, the tree line is actually moving up. So the people have estimated that the upward shift in the south and the north slope of Nanda Devi Biosphere Reserve was around 9 and 7 meters per decade. And many of the alpine meadows have shrunk significantly in the past 48 years. Another aspect is the biodiversity. How this climate change is going to influence this biodiversity. But before we estimate the loss or gain in the biodiversity as a result of climate change, we have to first estimate it. And if we have to count the individual species, it's not possible, because it's estimated that the extinction of the species will basically outstrip the exploration and discovery of new species, or estimation or counting of the species. So we are using space-based technology. We have derived a method to characterize the biodiversity at a landscape level. So here we have used the satellite data to provide the vegetation map, and using the top-down and bottom-up approach. So we have also had a field plot data of around more than 16,500 field plots, which has actually helped us to characterize the biodiversity distribution or biological richness distribution across the landscape. And this effort has basically provided us a baseline information upon which the future generation like you can build up and estimate the changes which are taking place in this region because of the climate change. And taking it further, I think many of you know about the biodiversity hotspots. Presently, there are 36 biodiversity hotspots across the world, and they are mostly distributed in the tropical regions. And if we define a biodiversity hotspot, basically it is defined as an area which has around 5% of the higher plants species, 5% of the higher plant species of the entire globe, and which has lost more than 70% of its original vegetation cover. So this is basically the definition of a biodiversity hotspot. And if we see, most of the areas which are biodiversity hotspot are also huge anthropogenic pressure, because they are the regions which are actually habitable across the world. So these are some of the biodiversity hotspots. As we see this on the left, we have the Madagascar, then we have the Western Ghats, and the Atlantic forest of Brazil. The concept that these areas have actually lost more than 70% of its natural vegetation cover means these areas are under tremendous anthropogenic pressure. Another aspect which influences the climate change is the carbon, its source and its sink, and the distribution of the carbon across the world. So when we see it, you can see most of the carbon is actually stored either in the temperate region, because this is the region where you have very less decomposition, and most of the carbon which is fixed either goes into the soil as peat and is stored there for centuries together. And we have the tropical region, which are basically the sink because of the dense tropical forests in this region. So this provides us critical information about the role of the various ecosystems, natural ecosystems, which act as a carbon sink, and where these areas can be conserved so that the modulation of the atmospheric carbon can be sustained. Similarly, India, we also have prepared an extensive high-resolution map of the terrestrial carbon stock in India. And you can see most of the areas which have a high vegetation cover are the areas where we have the highest terrestrial carbon stock in India. But the carbon dioxide can also be measured from the various sensors which we have put on the satellite platforms in space. For example, we have various databases which basically shows us the carbon flux and their inversion capabilities from space-based platform. So the advantages what we have of the carbon measurement from space, like we have the OCO, which provides us the carbon dioxide concentration. It has a global coverage, and with a relatively high spatial resolution of like 4 degrees into 5 degrees. And they have a coverage from based from weekly to monthly time scale, and the precision of measurement is quite high. It's around 1 ppm is their precision, which is basically around 0.3% error. And now various advanced modeling tools have also been developed to retrieve the carbon measurement from the satellite-based observations, and various extensive model programs are being carried out to basically improve upon these various models to validate and bias removal of these databases. And a very important aspect is the dynamic global vegetation models, which are basically the plant biogeography and vegetation dynamic models, and they provide information on the various vegetation types, their functioning, and their interaction with the climate to provide important inputs to the various climate models. And this is how we basically improve upon these. That's how the plant functional types are changing in the particular area, and all these have been done using TGVM. Another area which is important for the climate change is the natural disasters, where space technology plays a very, very important role. And because of the coupling of the climate variability as well as the anthropogenic impact, the disaster cycle is the climate change is important in the disaster cycle. One of the very, very spectacular impact is that of the fire activities. It is observed that because of the warming and drying in the global ecosystems, because of climate change, the fire activities across the various ecosystems have increased over the last few decades. And this global warming is going to result in increased fire activities in the future. So you can see that the various models have actually shown that there will be a large-scale increase in the global fire incidences at around 1.8 degrees centigrade warming. And the areas like Central Indian region, some parts of Africa and Latin America are going to see the number of fire incidences or the frequency of fire incidences more than 1,000 times the baseline, which is basically the 1850. And the change in the fire incidences vis-a-vis temperature regime can be very well proved from the satellite-based observations of the land surface temperature and the number of active fires. So you can see this is basically the data of 2010, although we have been doing this for all the years. You can see that the land surface temperature across the country in January is basically low, and most of the temperature is significantly high in the southern region. So you have a number of fires in the southern part of the country. But as it progresses in March, most of the central part as well as the southern part and the eastern part have a significantly higher temperature. And this results in the drying of this vegetation there, and you have a large number of fire in the central part of the country. By April, the fire actually moves from south to northern region. And in May, it's mostly concentrated in the north. By June, due to the onset of monsoon, the fire activity stops. So this is basically this shows a direct correlation between the forest fire activities and the temperature regimes. So if we see at a glance the hotspot of forest fires across the world, say during a week in March, it shows somewhat observations like what we see here. It's mostly concentrated around the tropics and in the equator, in the areas which are dominated by the deciduous vegetation, and some parts of the the equatorial region, mainly in the Latin America. When we go to this autumn, that is during September, October, this basically moves to south. There are another areas where space technology play a significant role is basically the estimation of the sea level rise. So using the digital elevation model and temporal databases, we are able to identify that due to the increase in the sea level, what will be the inundation in many of the areas. And some of the islands like Maldives, Malé, they are just a few meters above the surface sea level. And these islands will basically disappear if, due to climate change, the polar ice caps melt. And in the geological past, we have observed the sea level increase by around 5 to 10 meters. So this is actually an area of concern. So how do we go out? We have to conserve our ecosystem and conserve it in such a way that we are able to mitigate the impacts of the climate change on our ecosystems. So space-based information will provide us the basically a snapshot of the state of the Earth's surface at a particular time. And using various models, we can generate the information on the various interaction and other aspects to identify the areas which has to be conserved and protected, to basically carry out the protection and conservation of the area. With this, I end this presentation. Thank you very much.